Right, so we're going to pick up where we left off in these notes. And so we are still on day one, and we had talked about the Lagrange error bound and that Taylor polynomial, and using the Taylor polynomial, a polynomial to approximate any type of function like e and sines and things that we can't just normally plug in things by hand and find. And now we can find some pretty dang good numerical approximations. So today we're going to go and look at that Taylor polynomial a little bit more. And this type of problem I call the matching problem. So on the matching problem, it says like maybe we want to find what f of 2 is. Well, f of 2 isn't too bad. It would have been located kind of like right there in that part, which is just the constant because there's no x values to any degrees by it. So I call this matching by saying set this equal to this. Boom. And then you have f of 2. Well, that's really, these two first ones are the easier ones, and then it gets a little bit more challenging, okay? So I do not see any first degrees going on. Agreed? So if I don't see them, then I know that the f prime of 2 had to have been 0 or something would have been there. So I can set those two equal. Okay, so here's where it gets a little bit more fun. This right here in front of the second degree has been simplified because I don't see factorials. Okay, so that's already been simplified. So we're going to have to say, well, it was simplified from this right here. So I'm going to match by setting kind of those two guys equal at the 2 in this case, okay? And I'm going to have to go solve for f double prime of 2. So I set the -4 equal to that general statement. And now if I want to find what f double prime of 2 is, I can take -4 times 2 factorial. Same thing with that third derivative. This has been simplified. So I'm going to set it equal to what it would have been with all the factorials. Biggest mistake that kiddos make on the test is they forget about the factorial for like second degrees and above, okay? Because you don't see them on the 0 and the first degrees. So I set those two equal. So the third derivative of 2 had to have been 3 times 3 factorial, which would be 3 times 6, and that is 18. So don't forget factorials when you are matching. And when you have a problem like this, again, I'm going to be like, this is a matching problem. Don't forget factorials. That's what I'm referring to as this section right here. So let's see a problem. Here was a Taylor polynomial, and I can see that, oh, the first derivative and the third derivative had to have been zeros automatically. There is my just f of 0, but it asked me for f of 4. So I have to match what that has already been reduced from. So remember that this guy right here had a factorial before they reduced it to the 6. So if I want to know just what the fourth derivative was before everything was reduced, then now I have to multiply this 6 times 4 factorial. Okay, so now we actually have to go work this out because they didn't give it in factorial form. So 4 times 3 times 2, 12 times 2 is 24, times my 6, 24, 2, 12, 144. Okay? So that's what I call a matching problem. So let's look at this one, and I want to see if you can do this one on your own with the matching, okay? So first, that's easy. Boom, they have it. Second one that we would look at, that's easy because there's no factorials there. So, Look, though, they already had lots of times they just put it all in for the first two. So now do you see how they're going to always have this 2 and -3 as a distractor? That's not it, though. So go see if you can find what the right answer is, and I will wait by you pausing me, and then unpause. And see if you get C. So I had to take the second derivative of 0 over 2 factorial for the second part here, the second degree, and set it equal to 2. So the second derivative at 0 would be 4. So I can see that that one's out. So now we're left with those two. So the third derivative of 0 over 3 factorial has been reduced to -3. So that third derivative at 0 would be -3 times 3 factorial is 6, which is -18. So C is where I got my answer. Okay, this is one where they're kind of just giving you what those are, and they want you to write it. We are centered about 3. So if we're centered at 3, these guys are out because they are centered at 0. So that's the first thing I'm just going to kind of use. Hey, I'm centered at 3. So all of those are centered at 3. Then they give me these guys. See how the 2 and the, and like the first derivative, the 2 and the -1, they're all the same. So they're kind of like, hey, they're not really helping you much by those two. They're almost trying to trick you. Because then they're saying the third derivative is 6. But remember that 6, when we plug it in, had to be over the 2 factorial, which would have reduced to 3. So that one's out. And then again, they're giving me this 12, but the 12 had to have been over 3 factorial. And then they're even trying to say 12 divided by 3 is 4, but that's not really a 3, that's a 6, 3 factorial, which would be 2. So E is our right answer here. So on these, you just have to be careful with the factorials. Now, what I love about these is when they are asking you about local extrema and that you don't really even have to take a lot of derivatives, you've already taken the derivatives. So if I can see that the first derivative was 0, and remember we said kind of back on that one example, like right here, no first derivative, right? So I knew the first derivative had to have been 0, aka a critical number. So when I see that first derivative is 0, oh, guess what? Wherever we're centered had to have been like probably a relative max, relative min, or point of inflection. So here, when I can see that the first derivative is 0, I have a critical point. If I then go find the second derivative, if the second derivative is less than 0, remember concave down, then I have a relative max. And if the second derivative is greater than 0, concave up, I have a relative min. So we can use these Taylor polynomials to know if where we're centered at is a local max or a local min. So cool for the original function. Okay. Now, if the second derivative is 0, then it's probably a point of inflection, right? Since we don't know, we can't use this test. We learned that back in Calc AP. Okay, so let's go do this one. So here is the Taylor approximation for this function. They don't even make you go do it. They just said, I've done that for you. Thank you. All right, so here's my Taylor, and I want to know at 0, well, are we centered at 0? Because hold on, I don't know anything about this function except for where I'm centered. Yes, I am centered at 0. Okay, so at 0, so I want to know if I have a relative max, relative min, or if I can't tell. Well, look, I don't see any first derivatives, which meant that the first derivative at 0 had to have been 0 when they simplified. So I know I have a critical number here, okay? Then I'm going to go look at the second derivative. So f double prime of 0 over the 2 factorial, and however they have wrote that, is equal to 1 over 4 factorial. So they simplified that answer to 1 over 4 factorial, which is okay. I mean, they can simplify it lots of ways. So that second derivative is 2 factorial over 4 factorial. We don't have to go simplify it or anything. We just need to know that, hey, that is a positive answer, which means that we are concave up. So if I have a critical number and I am concave up, then I know that that function, which was f of x, has a relative min, because we're concave up, at x equals where we are centered, which is 0. So this is, I've seen this type of question on lots of AP tests where they ask about this. So really make sure you have this down before your quiz. Okay, and we can talk about it more in class if you need to. But there's the end of day 1.